I'm also going to record the one I do Thursday. I don't remember when my classes are. And so whatever one is better out of the two, I bet you the Thursday one will be a bit better because it'll be the second time I'm doing this. I'll upload that one and send it because this one will have so much content that you guys will probably want to rewatch it. So I just kind of want to start off by giving a quick overview of what we're doing today. So we're going to quickly, about halfway through, we're going to talk about assignment. I'm not going to talk about the beginning. We're just going to go through some really simple stuff here with some memory map labels. We're going to fill out this table here. And then we're going to go down here. We're going to talk about a bit more memory stuff. We're going to take a short break, about probably 20, 30 minutes in. I may do this break a bit later on, and I just kind of want you guys to think about ways you could write this. Maybe you guys can sit down, spend 5-10 minutes trying to write this equation out in MIPS, see how short you can make it, and then we can talk about other ways that we can make it shorter, because it will be a bit of a longer shoot. So I want to give everyone a bit of a mental break where they can kind of go stand up, walk around the room, think about it before they sit back down. So we may do this a bit later, depends on timing, right? We'll do about halfway through my quotation marks shoot in my head, which is probably about 40 minutes in. And then we've got large multiplication here too. So we're going to talk about how do we do large multiplication. I've got the answer here because I don't want to really do it because it's not actually important. I don't think I've ever seen an exam question requiring the knowledge of this. And then it's pretty simple once you kind of do it. So we'll just kind of go through the code, explain what it does, explain why we want it, explain how we use it, and then that'll be it. And then we go arrays, and we spend a lot of time in arrays, hopefully about at least half the time. So we're going to be looking at some very simple examples. I'm going to talk about the stack a lot. We're going to go into a lot of depth there. And then, sure. And then once that's all done, what we'll do is we're going to go into this final example here where we talk about function calls. We're just going to look at a very simple function call, like a Fibonacci sequence. And then we're going to build an entire linked list in MIPS using the stack. So we're going to cheat a bit. So we can't, because obviously we can't use malloc in MIPS right now. Yes, we'll talk about alignment in the very first section. And so building a linked list in MIPS requires a lot of hacks and stuff like that, but the whole point there is the function based, and you can kind of understand how the stack works and how we can use it. And it's just kind of, it's going to be like a 200-line program that will probably take about 30 minutes to write, and it's going to kind of use everything that we've learned so far up to this point and kind of wrap it all up really nicely. And not only that, we'll also be looking at function pointers, which is not something that you need to know for this course, but kind of will help you understand what a function really is in assembly if we actually look at how to implement a function pointer in assembly. And so once you kind of understand what that is, it kind of makes a bit more sense. Okay, so now we've done all that, let's just begin. That's an awfully cold day. So we're going to begin by talking about data segments and alignment, and I don't really know what I would call these. I guess space specifiers. It doesn't really matter. Directives is probably good enough. So first thing is text and data, right? This is kind of an important question. So text is for code, data is for readable and writable memory, right? That's the only distinction you really know right now. In real MIPS, there's a bunch more sections. So there's something called K data, which is for kernel data. There's read-only data. There's a few others too. There's I don't know if you can. I know the stack is a data segment. It's not data segment, but it's like a segment. But I don't actually know if you can access the stack as a segment and like write initial memory to it. I don't remember. But there's a bunch of other stuff you can do, such as I think it's probably about 5 of these in real MIPS. But you guys only have to care about 2. You need data, text, and data, and you can presume the data is read and write. I think if you go R data, I think it will give you an error if you try to compile SPIM with it, because SPIM is a subset. Anyway, doesn't really matter. But those are the 2 ones you care about, and these are the 2 cases, right? So if you want a bunch of data, use data. If you want to put a bunch of code, use text. Now, whenever you start running your code in MIPS, the first thing you notice is that we don't start it with a .text, and the reason why is because the .text is implicit. Every program is automatically started with a .text. Okay, the next thing is these ones here. Now, these ones here are just basically allowing you to declare chunks of memory, and that's it. So all you're basically saying is, for example, if you say a word, you're saying that you want 4 bytes memory. And so what will happen is it will allocate 4 bytes of addresses, and place the value that you give it into that chunk. So here, as you can see here with A, we have this contents here. I mean, let's fill this out. I'll have to go to a sheet for it. That's fun. Okay, I'll find the sheet. And so, for example, for A, here, the value is 42. It's going to be at this starting address, which is just kind of some random starting address that I just chose. I believe that's probably the top of the stack. If that probably makes sense. And so what that means is that the next value, right, which is in this case, wrong count, switch into the actual count. And in this case, it is B, right? And the value of B, okay, found it, and we can move it back. Wonderful. And the value B here, right? This is going to have, an address of 4 more than this, or rather 8 bytes, 4 bytes more than this, right? Because that's the one thing that's kind of confusing is that even though each byte is like 8 bits, right? The actual address is byte based. So you can only address bytes, you can't address bits. And we know why, right? Because, for example, with like bitwise arithmetic, that's how we address bits. So if we want to grab like the second bit, we can't just use like an index. There's no address for it. We have to like grab the entire byte and then just extract the bit we want. And that's mainly just to give us a larger range. We get 8 times the range because we really rarely care. And so the contents of this address is, as you can see here, this is just going to be space. So this is not putting 4. It's just asking for 4 bytes of space. Okay. So it's just going to be whatever was currently there is still there. It's not going to change anything. So then the value of C, right, is going to be right after that. And it's going to have an address of, and hopefully this one is a bit obvious, it's just going to be 8, right? 28, because it's just going to be 4 bytes more than the previous one, and there it is. Now this is where it gets a bit tricky. So the one thing we say here is that we're going to put an ASCII number, and it's going to be ABCD, right? So how does this look in terms of memory, right? Well, we can fill out the first few. We can fill out the starting address, right? We know it's 2A, and we know it's going to be like, we know there's going to be A, we know there's going to be B, we know there's going to be C, and we know there's going to be D, right? And what we can do is we can decide and go, okay, let's make it a bit bigger. We can go, okay, we'll just put every byte. So we'll just, wait, what? I'll just put a slash there so this appears, because I want this. So weird. And so what I want here is I want like each byte 1 by 1 because, or each word I should say 1 by 1, because if you put more than one word to a label, it kind of gets confusing. So what we'll do is on the next line, we'll put like the next part of the word. So we know that the next word will start at, 4 more. And so this kind of is probably where it gets confusing. So if you go A plus 4, what do you get? We get 12, right? And so 10 is A, B is 11, C is 12. So it's going to be 2C. Okay, and then we can just put in our other addresses, which we'll have to put the slash here just for the sake of it, and then /0, and then the other 2 values in this value here will be determined by the alignment. Now, what do we mean by alignment? And this was just, obviously, Paul just asked the question before, but to clarify alignment. And so alignment is actually, it's due to how computers work. So computers work based on 2 systems, right? So the first system is they have something called a bus, right? And a bus is just kind of like it's kind of like a real world bus, right? You put like people on it and you move it around. In like computers, the bus also puts things on it and moves around, right? So this is kind of like one long, you can think of it like a long wire. It's not really necessarily a wire. It's like it's basically it effectively is implemented kind of like a wire and typically is a wire, but it's got a lot more to it than just like a strip of metal. And so effectively what happens is your electrons, right, your packets of your data move up and down this kind of bus, right? And effectively that allows you to kind of send messages between your systems, right? And the bus has something called a bus width, right? And this is basically how much memory, the bandwidth, if you can think of it in terms of like a network, right? The bandwidth of your connections, like how much you can upload at any time. The bandwidth of the bus is how much you can push at any time. And so in this case, the bandwidth of our bus would be like 30 bits if we're in a 30-bit system, which we are. If it's your own computer, it'd be 64 bits. And sometimes you can have bigger buses than your system. Sometimes you have smaller buses in your system. So for example, I don't know the name of it, but there's a 16-bit computer. I think it's like the 6502 off the top of my head. I may be wrong. And how it works is it's a computer that's 16 bits, so it's got a 16-bit bus, but it actually can address up to two 16-bit chunks. So how it works is technically like 17-bit, I guess you could say. So there's two 16-bit chunks in memory, right? And that means every address has two values, and then you tell the CPU when you want to switch what address you're talking about. So you can like switch between the two chunks. And that's like a typical case of what's called a non-linear address space, because your memory isn't laid out like flat. It's like two chunks of memory laid on top of each other. And you can switch between the layers. Um, is memory allocation always contiguous? No, but you can boom. It's always contiguous. So the OS will give you memory allocations that you can presume are contiguous, even though they may not be. So how that works is something called pages and virtual addresses, which you'll learn very soon on. Very, very soon. I think a week, 2 weeks, you'll learn about virtual addresses. I think. I don't know if this course teaches virtual addresses. It teaches like OS stuff, so it probably does. And so when you learn about virtual addresses, if you don't, I'll cover it later on. You'll learn that they aren't actually necessarily contiguous. So how it works is the computer like splits up the memory into something called pages, which is like pages of a book, right? And so every page can have different amounts of memory on it. And so what happens is when you ask for, let's say, I don't know, 2 MB of memory, it will split that up into pages, and each page can actually have a different physical address. And so what it means is that even though your computer is looking at it as like one big contiguous virtual address, it will be split up into multiple sub pages which have different physical addresses, right? So it's kind of like an indirect table where you kind of have like your virtual addresses here, right? And these kind of get filtered into physical addresses that could have different values. Right? It's just like it's like a table, and then you can have multiple interaction on that. So you can have like two interaction where you have like a virtual address to like a kind of a physical address, but there's like two layers of it. It gets very complicated. I'm not going to go through that. But the rough idea is that you can presume it's contiguous, right? That's the reason why we have all these complex things, is so that you guys can presume it's contiguous when we're programming. Which makes life a lot easier, and it makes things faster too. And most of your memory will be contiguous anyway if it's within a page. Okay, so we have these allocations here. Then we talk about alignment, right? And so the thing is that with buses and stuff, is that when we want to address certain parts of memory, those parts of memory are effectively grouped by their address, right? If that kind of makes sense. So for example, if you have a 2 byte bit in memory, let's say like a short integer or 2 characters, then that bit of memory will have to be addressable by the size of its largest member. So if you have, for example, 2 characters, like character A and character B, the size of the largest member here is 1, so the memory has to be addressable by 1, right? So really that's anything, right? But if I had an int, for example, A, and a character called B, right, then my largest member here is A, so my memory has to be addressable by 4, right? So what that means is every 4 bytes, A has to be placed on. So A could be placed on like 0x4, it could be placed on like 0x8, 0x16, it can't be placed on like 0x14, right? This has to be addressable. But sorry, that was I thought of decimal in my head and then wrote the decimal without converting to binary. So it could be stored as 0x10, it could be stored as 0x04, 0x08, right? Because obviously this is 16. But it can't be stored as like 0xf. It can't be stored as like 0x. I gave 14, which would be D. No, it would be E, 0xe. So the point is it has to be addressable by the like modulus of this number, the size of this, right? And the reason why is just purely a performance thing. And I believe old MIPS computers can't actually address. If you try to address in SPIM by an invalid alignment, it will give you an error. However, if you do it on your own computer, it probably won't, because x86 does allow it with quite a bit of leniency. And ARM does allow it now. So if you're doing if you had like your mobile and you did it, it probably would work with a small performance downgrade, depending on how old your mobile phone was. If you've got a very old ARM thing, that may not work. You make like a hardware exception. And the rest of these things will just be, these other 2 bytes here will just be the null here, right? And so the hex of this will be, I guess it'll be 6-1, right, for this. Oh, no, it wouldn't be. It'd be whatever the hex value of A is. Oh, yeah, it is a 6-1. And 6-2 and 6-3 and 6-4, right? And then these values would be 6-5, 0, and the other 2 values would just be this. That makes sense. Right? Okay. So does that kind of make sense for like alignment? Is that you want it to be like it's like it's talking about the memory address, right? So you're saying the memory address has to have like a modulus of that alignment. So if you have an alignment of 2, right? Then that means that if you're aligning by 2 bytes, I should say. So if we're aligning by 2 bytes, that means the memory address must be modulus by 2. Because our memory address is in terms of bytes. So when we did this alignment call here, right, what this is saying, and this is a lie that I hate how Spim does this, but this is actually 2 bytes. It's really confusing. I always get it wrong, but it's actually 2 to the power 4. So 2 to the power of n here. So this would be 2 to the power 2, which is 4. So when you have a line 2, it's saying, hey, align 2 to the power n, which n in this case is 2, so that will be memory address %4, right? And that is very confusing because it kind of doesn't necessarily make sense. I would prefer this to be byte-based, but they've probably got reasons. Especially since you can, I guess the reason why is that you can't, this always has to be a multiple of 2 is the explanation, because it does. You can't address by like any other value. You can't address by like 3 bytes. That doesn't make sense. So I guess that's the reason behind it, is to force this to be a multiple of 2 so that you don't have to have like hardware exceptions and stuff if they give you like a wrong alignment. That's fair. So here when we say align by 2, we're saying align by 4 bytes. And so what's happening here is if we didn't have that align 2, what could happen is if we forcefully forced it to be, and so we'd have to say align 0 here to force it to be on 1. Actually, these are bytes, so it doesn't really matter. So if we remove this, let's say we remove this alignment here, then these bytes don't have to be aligned in this boundary here. So what will happen is it will just do this, and then it will just do 1, 0, 0, 1, 0, 0, 2. It'll add bytes to this because there's 2 here, and so this will be E, and this would be the values here, right? So this would be 1, 2, 3, 4. So 1, 2, 3, 4. And that'd be my 4 bytes. Okay. However, in this case, because we have the alignment of 2, it means that these have to be a multiple of 4. And so if we look at the value here and we go OX11, and it won't like me because it's thinking it's doing math. So let's to do it for us. Yep, and that's the value. And so we go, this is modulus by 4. We find that there's a remainder, so it's not divisible, which means that we need to add this remainder to the value. So we're going to add 2 to the memory address such that it is divisible. So in this case, to add 2, this goes to F, and this goes 3. That's the value, if that makes sense. Okay, I'll just erase for the rest of it because the rest of it's less important. So these words, and this alignment only applies to the next item, so it only apply to this 1 here. It won't apply to the 2, it won't apply to the 3, and it won't apply to the 4. It only applies to the 1. And then we have the word here, which is just everything has to be 4 bytes. So this is just going to be hopefully somewhat similar, right? I think I forgot 0 because it doesn't line up. 1, 0, 0, 1, 0, 3, 4. Yeah, that should be like that. Yeah, okay. I don't know why I looked at so I don't know why that took me so long to realize that. Okay, so then that's just gonna be a 1, and then we got 2, we got 3, and then Oh, okay, this is wrong. This is right. And so this is going to be OX10010038, and then OX10010003C, and then I guess just 4. So it's basically going to be exactly what we had before. So then we can just copy and paste this here, and this will just be 4. And then this value of F is just going to be, I'll go back to it, but it's just going to be this. And I mean, I can show you the memory if I want. Okay. Then I guess we'll give these actual proper values. So this will be D and this will be E. If we look at F here, it was just one single byte at the very end, and so it's just one single byte, right? It's just going to be +4 because this is 4 bytes, right? So let me just format this nicely, and then we can refresh the frame so we get the updated version. Okay, so now that's done, we can just kind of continue on. I don't really want to waste too much more time with that, but I felt that was needed as an explanation. Okay. I'm going to come back to this, and we're going to look at this as we go through the examples, right? So this is kind of going to be like our referred of the different ways that we can address things. I mean, you guys hopefully know what this one is, right? So this one is obviously if we're loading in a string, we use load address, right? This one is if we want to load in, you've just probably started seeing these ones here, but just kind of cover them. This one's for loading in a word, right? So as you can see here, if we load in this word here, we're just going to load in all these numbers. Why? Well, because if we look up here with A, B, C, D, right? This is our word here. This is what we're going to load in. So we're going to load in this value here, the 616266364. Okay. And so that's what the value of this will be, because it's going to load in the kind of like, if you interpreted the data as an integer, what is it, right? And then obviously that you can still print that out as a string, right? Because that's kind of the weird thing about assembly is that like you could grab it like an integer, right? And you could still treat it like as a string, but it had to be like an array rather than directly a string, because rather than having like a pointer to an array, which is typically what a string is, right? You have like a pointer to like the first element and so on. An integer kind of is like an array of them, as in that like contains it within itself. It's like 4 characters within itself. And LB for loading bytes. So if I just load a single byte here, I'm just going to get A. And you can do things like you can add to the address. You can see here, we can add 1, and that will give me B. We can add 2 to get C, and so on, right? And then here we can load the address of A, right, into T0. And I think that should be T0 here, not T1. But if this is T0 here, then what it will do is it will add 8 to the result of this. So it will find A, then add 8, which will make it go to 1, 2, so 1, 2, 3, 4, 5, 6, 7, 8. It'll get to I. And so the value of this as a byte will be I. If that makes sense, right? Because these are loaded right after each other. And no, I've just used ASCII here because I didn't want to deal with the /0, because the /0 makes this question a bit harder. And then finally, we have one final thing. You can only use this only if this is a constant. If this isn't a constant, if this is a variable like this, you have to use this. But yes, and you can't use like a variable. You can't use I. So you can use it as like a constant kind of access. But so if you always want to access the 0 element, it'll work. If you always want to access the 3rd element, it'll work. But if you have like an I counter that increments, you have to use like a different way of doing it. And you'll see what that way is. If you're dealing with something like x86, it's much more complicated, and it's great because in x86 you can do things like you can like multiply by like a value, so you can like multiply by 2 to the power of something, right? And that's what happens with CISC. So I talked about CISC last week. And so often CISC computers allow you to do some crazy awesome stuff where you can like multiply by different values, add, subtract, you can do all this like crazy addition. But the instruction gets very complicated. Whereas stuff like this, where it's RISC, right? It's simple, right? So keeping it simple, keeping the size of your instructions small, keeping them all the same sized, and so on. Okay, and then finally here we've got the same kind of idea. We're loading AA here, and we're loading in the word, and this should be T0 again, and we're loading in word +2, and so it's going to go 1, 2, so 1, 2. I don't know why I counted A there, and so that's going to be C. I can highlight it. There we go. But the problem here is this is what I was showing about before with memory alignment, right? So if it wants to load a word, this has to be aligned by 4 bytes. But this isn't going to be aligned by 4 bytes, not necessarily, right? It could be, right? It definitely could be. Like we could just luck out because all of these have to be is aligned by 1 byte. So this could be on like the 5th byte. Sorry, this could be on the 6th byte. This could be on the 7th byte. This could be on the 8th byte. That's okay. Or it could be like 1, 2, 3, 4, 2, 3, 4, right? But most likely it isn't going to be. It's just going to be like, I mean, you only got like a 1 in 4 chance of it being. And so if you run it, I mean, it may work, but I presume it won't because I presume the memory is going to start like a 0 value, which means that this would have like a offset of 1, this would have an offset of 2, and this would have an offset of 3, which would make this not be divisible by 4, which would cause it to occur to be a misalignment, and you'll get a misalignment error because this MIPS that we're using doesn't allow you to misalign memory, which is actually kind of a lie. You can still misalign memory, and you can still abuse it in very specific cases that make your final exams a little bit easier. And I'll talk about this later on. But for now, just don't. Just always align things that need to be aligned. So the tip is that if you're going to create a word here, go ahead. You can line it like this. That's fine. If you're going to create an array of words, right? So say we're going to create like 80 words, right? Then we're going to create space. Let's say 80. But before we do that, we need to align that. And so we'll align that space 80 by 2, right? Which is going to align it by 4 bytes, if that makes sense. So for example, you'd write it like, oh, it's here. Okay. No, that's the wrong one. Oh, there's the right one. I don't know what I'm looking at. Okay, so here's my LL here, and let's create a sample one, just show up. And so if we just do, I don't remember what we was looking at. We're doing this, okay. So let's say we've got a data segment, and we want to create, as I said, I think it was 80 bytes of memory. We could do this. Before we did that, we would also have to align it by the size. And so if we aligned it by 2 here, you can see I wrote 4, it's still in the habit. Then this would be like aligned by the power of 2, which equals 4. So this would be every address would have an alignment of 4, right? Or rather the first one would, but because they're all following each other, they technically all do. And so what this means is this could hold, 20 integers, for example. It'll be fine. So when creating arrays, make sure you always align them, else you'll probably run into issues. It depends what you're doing for them. Okay, we'll leave the fun break for a little bit. I'm just gonna cover large multiplication arrays, then we'll come back to the fun break. And it's not really that fun. It's just like a break where you can think about how you do it in your head, or you can write it out, and then we can come back and see whether or not people have different ways of doing it. The course does have 3 answers for this, and I actually think all 3 answers. There's one of them that's pretty good, but the other 2 are kind of like there's a better way of doing them. So for example, with this, you're trying to reduce the number of instructions or registers. And we'll look at this question later on, we'll talk about it. And I think the course says like 3 is the minimum, but that's not actually true. You can do it in 2. You can probably do it in 1 based on some experience with how that's typically going to work. I just couldn't figure out doing it in 1. Anyway, so we have this stuff here. We have large multiplication. For example, these values here could overflow an integer if y is large enough. So how do we do the multiplication? And the answer is in MIPS, when you multiply things, how it actually works is there's actually both a high and a low register, and these are hidden to you. So you can't access these high and low registers at all, and so they're hidden away from you. The only way you can access it is through these commands. They're not like registers that you can go like $low equals, right? And so what happens is whenever you do multiplication, it always does this, and it puts the low 32 bits into this low and the high 32 bits into this high, right? And so when you write it like this is how it looks. But what typically you'll find is that when you write multiplication, you typically write it like this, right? You go multiplication, I don't know, T0, T0, T0. What effectively it's going to do is it's going to do this followed by this. I never remember the command. It's mflow. Okay. And it's going to do this. That's all it's doing. It's doing a multiplication, then just taking the low part of that multiplication, right? And so this is saying what register to put the low part in. And so it's going to multiply T0 by T0, put that into high low, and then take the low part. So it's just like a shortcut. but you can do it manually, and that lets you get the high part and the low part, right? And we notice here that when we're writing these high and low parts to x, right, we write the high part to x, the low part to x plus 4, i.e. the high part's the upper 32 bits, and the low part is the lower 32 bits, or the lower 4 bytes. Okay. And the rest of this is just the syscore, and you're just doing your add instructions. This is the only part that we really care about. So as I said, this is pretty straightforward. So you don't really need it. You can kind of forget about it. I presume maybe have like a note somewhere. So if it turns out there's a question on this in the exam, like it's easy to refer to. But like very rarely you will have to handle like this kind of multiplication. So let's talk about arrays. And then we'll talk about bit about assignment. And then we'll probably stop about, I don't know, 10, and then we can have the break, and then we'll come back and we'll do to about 10:30. I'm thinking to finish the function part, so you can get fully set up for your assignment. And you can do it because you want functions in your assignments, and so being able to know about prologues and stuff like that is useful. I know you've covered them in lectures, but it's nice to see them in reality a bit and to hear about like when you should use which one and so on. Okay, so let's just begin with a very simple example. We're just going to translate this code to MIPS. So let's begin with the max.s. So what we're first going to do is pull this over to the side here. We're going to remove this, then we're going to create a new one. Do this. This can have our code here. It can be C. Okay, great. So then we have this max here. So let's begin with our max of array. Let's begin with our main function, right? We can add our var variable at the bottom, our return value at the bottom. We can add, I guess we can do this. And wonderful. Okay, it's at a data segment, and we need all this stuff in data, or rather this in data. So how do we do that? Well, we got to talk about how many numbers we want, right? So if we want 10 numbers here, we got to store 10 numbers in the data segments. So where do we store it? Well, we can just put it like right here, and we can literally just go something like dot word 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will store 10 numbers in data. That's it. Now we could add a line 2, right? We should add a line 2, right? Things will typically be aligned by 32 bits anyway, so it's not necessarily necessary, but it's still nice to do, right? Just to kind of really make sure that you're really clarifying what the alignment is, and you're making sure there's no problems. It just will kind of help you in the short run as you're kind of learning this stuff. So let's begin with an LI, and we'll load in I equals 0, and we'll load in other numbers. So let me get these are not 10 digits. These will be 10 integers. So each one's going to be 32 bits, one by one, right? So they are going to be just 32 numbers. So this will be like 16. So this 8, 12 will be the first value. Will be the second value. This will be the third value, and so on. Makes sense, right? They're literally like 32 bits worth of data right after each other. All right, they're not going to be it's not going to be a string, right? If you want a string of the numbers, you'd have to do like ASCII. Right? But remember, assembly doesn't really have the concept of strings or data. It's just like what you want to use it at for. So in this case, we're just going to use this as integers, right? So they would call them integers, but like in assembly, there's no real difference. We could use them as a string. It would be kind of fine. As long as we had a pointer that was valid. Let's load max as well. So we'll load max as S0, T1. We'll come back to stored registers later. And we'll set max to numbers of 0. Okay, so how do we do this? Well, this is actually pretty easy. We just say load word, right? So it's going to load word from an address. And so in this case, we can we load word directly from address? I always load into a variable. Let's see if I use it here. I use a variable. You can. Wonderful. Easy. Okay. It depends. Oh, so we needed it'd be nice to actually have a table for this. I typically always use a variable to load. Just it's what the compiler will convert it into, so it doesn't really matter, but just for simplicity. So we can just load the first number. So this is just going to be max equals number 0, right? Sometimes I will write it like this, make it clarified, and even sometimes you'll see me write it like this. These are both effectively the same thing. This is a hack. It's not really a hack, but it's like a nice little trick that the compiler will often use to get around the fact that you need to use registers for things. So like in reality, this has to be a register, right? And so what it can do is it can basically store it as an offset of the 0 register, and that allows it to get around the fact that it has to be a register. So we can store, actually we say I equals 1 here, so we might as well use 1 rather than 0. Obviously, just for reasons, you really have 0 here as the max, so there's no point to repeat that. And then we can just have our while loop here. And we can have end while. And we can just say bar I is less than 10. Okay, this is pretty easy. Yeah, remember we talked about this before. You change this to an if statement, you add your while here. Then you remove the statements here, right? And you change it to like a loop, right? And you can use unless and stuff like that. Stuff like that, right? Okay, so I'll just kind of do that in my head. Because it saves the time, you don't have that much time. No, you go away, and we'll just do this. So branch greater than equal, we'll just say if I or T0 is greater than 10, jump to this target. In this case, the target's going to be end while. Okay, then we can just say if I is greater than, I guess I'm just going to say while I is less than 10. That kind of reads a bit nicer. And then we would just do this using a simple jump. So the easiest way to do it is just to say, skip max, right? And so we can say, hey, branch if greater than. So if numbers of I is greater than max, so in this case, or if numbers of I is less than max, rather, we want to skip it. I did, right here. I said an alignment of 2 and a word. You don't, some people will write it like this. That's okay too. It doesn't really matter, right? The alignment of 2 isn't going to take up any space in memory. It just refers to the next part. So if numbers of I, we need to get numbers of I first. That's probably the most important part. So let's address numbers of I. So the way we can address it is we can go, okay, load me the address of, I'm just going to load it into T2. And we can probably save it us every time by not having to reload it every time. I'm just going to reload it every time. I'm going to keep it very simple for you guys. So we're just going to say, basically you're making a pointer. So this is what I always recommend is that you kind of want to use pointers rather than this stuff. So we'll look at how do we use these pointers to make this easier. But we're basically creating like a temporary pointer and we're setting it to numbers, right? And then we're going to add to that pointer and we're going to go, okay, hey, hey, when does this? Add to T2 and I want you to add I basically. So it's going to add I. But the problem is that I isn't actually correct because I is like an index and each number is 4 bytes. So we have to add 4 times I. So it means we first have to like multiply. We have to go like T3. You kind of how this gets confusing. Oh, wow, look at this. See what I was saying before? Confirms my suspicion. All right, I'm just going to write it this way. So T3, and then we can say T0 by 4, and so we're going to find offset of I in array, right? And then we're going to add the offset to our value. So T2 equals T2 plus T3, right? So we're basically going, temp is plus or equal to I times 4, right? Which is really just I if temp is an integer, right? Okay, and then all we have to do is we just have to actually load that value into memory. So the easiest way to load into memory is just load into like T4, right? Or we could load into like T2 or T whatever. I'm just going to use new variables for every single thing rather than reuse the old same ones because you guys are starting off. So to get used to how do you reuse the old values is a bit tricky. And so we're just going to say int temp2 equals numbers, right? Okay, wonderful. So and then what we're going to do is we're going to say, hey, if numbers of I is less than max, right, then jump to skip max. Okay, else what we're going to do is we're going to add set max to it. So we're going to say move, max from numbers of I, which is just going to be T4. So it's going to load numbers of I into max. It's equals numbers of I, right? And then regardless what happens, we're going to go to skip max, which is just going to be I++, right? So add I, and then we're just going to jump back up to R. And this is basically all we need, and this will find us the maximum of the array, right? It will loop over, we find the offset, then we add increment and so on. Now, if we have a different way of doing this, it would be to use pointers. And so in this case, what we'd do is instead of loading I, what we're going to do is we're going to load the address of number 0. So we're going to say T0 equals numbers, right? We're going to basically have like an integer pointer. Right? And then what we're going to do is we're going to load words from that integer pointer and each time increment that integer pointer by 4. So basically we're moving a pointer up and down rather than moving an index and doing all this. Because this is a very easy way to do it in C, but in actual assembly, it's a bit more annoying than just using pointers. So we're just going to have a same kind of while loop. The first thing that you'll notice is that we can't actually do like 10 here, right? Because it's not really 10. It's going to be like 40 plus the numbers address, right? But we can actually say that. So we can say, hey, branch greater than or equal P0 numbers plus 40. I'm going to say end while 2 and while 2. Right? And so we can say, while I guess we could say like current is less than numbers of 10 as an address. That's what we're effectively doing here. Okay. So we can do stuff like this, right? You could also like recalculate this. It doesn't really matter. And so this is going to be a constant number. This is going to be a constant number. So this is going to add them together, and that's going to be fine. Okay. And then all we have to do is we just have to load the word in that we were doing before into T1, right? So we can say something like, I don't know, int temp equals current. And then go, I guess we also need, the one thing I did forget was our maximum value. So that's just going to be numbers. This or just this, right? Again, it doesn't really matter. The compiler will translate it. You could also do it like this if you really want. Obviously, we have to put around brackets around it. What is we doing? Okay. So the next thing we want to do is we want to look at, so we're loading the word. This is going to load the current number. Great, fantastic. Okay, what do we do next? Well, what we can do next is we can, I've lost my train of thought. Okay, we just got to do this if statement. That's pretty easy. So we're just going to have like a skip max, same thing that we did before. And then we're just going to do, I++, but in this case, we're just going to do numbers plus 4. So plus 4. So it's just going to be current plus, right? So notice this is plus, but we've got to increment by 4. And the reason why is because this is an integer. So every time we increment, we've got to increment by the size of the value. C does that for us, but we have to do it when we don't have C doing it for us, I guess. So now we can just do a simple branch here. So this is going to be branch less than, right? So if T1 is less than, why is this numbers? This should be current. If our temporary value is less than our maximum value, which is going to be T1, so let's just use T2 here, which is obviously not reuse the same value. If our current value is less than our maximum, and then what we're going to do is we can just jump to skip max. Right, and then we can do skip set. And the one thing you notice here is that we're actually using a lot less variables. That's kind of nice. All right, this one used like 5. This one uses 3. So we're saving variables, and then we can just have like a jump right at the end. While we're also being simple. And if you want to test this out, you'd have to like swap the names of these two. This would have become like main and other. Right. Yeah, and so this will jump. I mean, there may be like small issues with this. Whenever I upload code, I test it before I upload it to make sure it works. But we don't really have time now to test it. So we'll just say this is the rough schedule, right? There may be like things like, like what I did here, right? Where I use the wrong variable, but I don't notice anything. If you guys notice anything, or tell me it doesn't work, look at it and figure out what's wrong, but it should be fine. Yeah, these statements are fine. This is a lot less instructions and it's a lot simpler, right? So you're grabbing the current value, you're finding the maximum by dereferencing the pointer, and then you're just moving the pointer while it's less than the address of the last element, and then you're loading the value. If you're jumping, if it's greater, and so on. And this is what your compiler actually will turn this into. The compiler's pretty smart. Okay. And then we got one more example I just want to go through, which I think is quite nice. And we're not going to use the integer indices one. You can do this if you want in your own time. But again, the integer indices one, I'll upload an example of it. It's going to look something like this, and it's going to be a lot more complicated, and it's going to put my head in. So instead, we're just going to do the one using pointers because it's a bit simpler, and it kind of demonstrates arrays a bit nicer. Actually, you know what? Your lab does kind of. Let's have a look at your lab quickly. I just want to make sure. If your lab uses integers for things rather than pointers, and it kind of forces you to use integers, then I will do the integer method just to make things easier. Return arrays. This doesn't require integers. Okay. Yeah, see here, you use pointers for this. If you want to use integers, you can. You can use pointers here. But that is a little bit less convenient. You can definitely use pointers here. And you probably should not use pointers here, but you can. I think we went through one example. I don't know. We'll just do integers. Why not? We'll keep it simple because I think the pointer method is a bit more complicated. So I presume that people are probably struggling with it more. So let's just keep it simple. Use integers. So we'll keep this as a value. We'll call this string.s. This is going to do a few things. It's going to find the load in a string from memory, from getchar, right, from SDN. And then once it's loaded in, it's going to find the length. And then it's going to print out the buffer as well. So our main function is going to be pretty simple. We do need a data section to put our string in. So we're going to need space for it. The space is 1025 because it's 1024 plus 1. We can say this is our string, which is going to be, I'm just going to call it buff. Right? Okay, wonderful. We have our jump. Okay, great. And then we can also have our I value here, right? So if we want to turn this into whatever we want, we probably want to use a while loop. Okay. And it's okay to have breaks here. And also I noted here that it returns EOF in kind of this EOF situation where you press Control D. So typically we won't ask you to do things to EOF because it's kind of hard and confusing. So we'll just say do to 0, which has the same value. I presume it's just how spin works for some reason. So we can use our I value here and we can just say like move, 0, 0, and that will give I equals 0. I guess you could also use a load immediate here, but I mean, it doesn't really matter, right? It's personal preference. We have a while loop, we have an end. So we're going to go, hey, while I is less than n length, so we can just say branch greater than equal, right? I is greater than equal to the length, which is going to be what? Well, we don't know what the length is. Probably we can just say 1025, right? So that's fine. Or length is going to be 1024 rather. The max size is going to be 1025. And we can just say jump to end. Right, so we can say like in this, we can go, wow. Wonderful. Okay. So we could even say 1024. We're going to read down our character. So we're going to say, load immediate B0. To load in a character, you can't really read character in SPM. So typically instead what we do is we load in an integer, which is going to be 5, I believe, off the top of my head. Let me just get up the thing to make sure I don't mistake that. Is it 5? Okay, wonderful. Okay. I'm just going to presume if you guys say it's 5. Okay, so this would just be scanf %d at char, right? So we are going to be loading in instead of loading a character, we're going to be loading in like 1 byte we're going to be loading like 4 bytes at a time, which is going to be a bit weird that you're going to have to give characters like integers. But like the idea still remains of what we're doing here, right? Is that we're still like loading in kind of a pseudo string. There is actually a string load function to read an entire string, but I don't want to do that because I kind of want to show off the loop. So the string load function cheats this entire while loop and it's just a single system call. But I kind of so maybe we'll change the question just slightly to say it's an integer buffer just to make it kind of clear. And then we'll do an integer buffer that's null terminated, sure. Right, that's fine, right? It doesn't really matter what we do. But by making integer buffer, this does change this. Now this has to be 1024 times 4, right? So instead what we're going to do is we're just going to make it still a character buffer, right? It's still going to be like 1 byte at a time, right? So what we're going to do is we're going to call this like we can still call this, I'm going to call it byte, and then I'm going to type def byte. So I'm going to say every character is just a byte, just to make this read a bit nicer. But so we're still storing like quotation marks characters, right? But we're storing them as like 0, 1, 2, 3, 4, right? So we're still printing out like a string, but we can think of it as we're storing it as bytes of this integer here, right? So when we like load and store bytes, we're always going to load and store the byte version of it, but if that makes sense. You'll see in a second. And so that means all we have to do is we just have to go, okay, if the character equals EOF or if the character equals 0, then we can jump to end. So, branch equal to 0, v0. I need a system call, don't I? To end. Okay, so if this is equal to 0, then jump to end. And all we're going to do is we're just going to index buffer. So we need an I variable. So we're just going to do the exact same thing that we're doing before, right? Multiply, I by 4, because, well, in this case, actually, I just said it, didn't I? I said this was byte buffered. If this is byte buffered, then we don't need multiply by 4. We can multiply it by 1, which obviously isn't going to do anything, right? We can just kind of remove this line, but I'll kind of keep it here just as commented out, just to kind of demonstrate. We need to multiply by size of the underlying data. In this case, we have just a bunch of bytes, right? So we'll multiply 8 bits, I guess you could say. Anyway, so that's fine. Then all we have to do is we just have to like load address st1 of our buffer. Just add. What we could do, I'll show you the trick in a second, but there's a trick around how we can like load addresses here because buffer is like constant. It kind of is quite nice. So we'll just use T2 here. Sure, it doesn't really matter. Actually, we'll use T1. We'll just like load the address of the buffer, then we'll add to it, and so we'll add T0. So this is going to find the address, the offset. Okay, so now we found the address including the offset. So now all we got to do is just load the byte or store the byte. In this case, we're storing because we're doing this, right? So in this case, we can store the byte, right? If we're storing an entire word, we use SW, but in this case, we're just storing a byte. So we're going to store T1. No, we're going to store T0 in T1. Right? Make sure that your order's right. You're storing this in this, or you're loading this into this. Okay, so we're storing this into T1, right? Simple as that. And instead of storing T0, we should store V0, right? Because this is the value from the system call here. This is our character. So we can just say, buffer var equals ch. Then we just do I++. Example took way too long. Jump to easy. And at the very end, we can just say buffer var equals 0. Now we still have an I variable from before, so you can just like basically repeat this step. Right? And instead of doing I++, we're just going to do store 0 in this. Right? So this is going to equal 0. Easy. Okay, so the next thing that we have to do is we have to reset I to 0. We're just going to reset I to 0. Right? Again, I equals 0. And then we're just going to do the second loop here, right? So this is going to be length, end length. It's just going to be branch. I guess we'll have to do this thing again where we have to like check whether or not we have to like load the value in. So we're gonna load the value in by doing this kind of step here, right? Instead of using LB, right, we're going to SB, we're going to use LB, and we're going to load this into like, let's say T2. Right, so what we're doing is we're going like temp equals buff of I. Then we'll have our I plus plus again. Over and over again. And then we can do something like here, we can go, okay, if this is equal to 0, then we jump. So if this is equal to 0, we're going to jump to end length. Wonderful, easy, okay. And so that's just going to loop over and over again. And then the very end, the length will be I, right? Simple as kind of standard C loop. So I'm just going to print out I, then buff. I'm not going to bother with the strings because it's kind of obvious. Maybe I'll just leave this out. You guys know how to print stuff out, so it's fine. Printing out I, then just printing buff. Right? Just keep cautious of time. So I'll just make sure I do this before I submit it or before I like push it, but you can leave that. Okay. And so there's a few things to notice here. The first thing is that we can use like iterators here and it's fine, but we could also use a pointer, and a pointer here would be much easier, right? And then I also mentioned the other thing before, how if we have this buffer here, we don't have to like load the address, then add. If all you're doing is adding to the address, then what you can actually do is you can just say something like this, load B into T2, buff of T0. Now, what does this actually mean? Well, this is saying load into temp, buffer plus T0. But T0 is just I, so it's just going to be this. Does that make sense? Like, you're kind of like, oh, I guess I should add like the dereference to make it clear that we're like dereferencing the result of this, right? And so it's going to do T0, which is just I, and this is going to be like the same kind of value. So these are going to be the exact same. So you can write it as 3 lines, or you can write it as 1. The reason why I kind of like to recommend to write it as 3 just at the beginning is because if you are multiplying it by a factor that isn't 1, you will have to do the steps. Well, yeah, you will. There's no way around it because you can't do something like temp equals buff plus 4 times I. In other languages, you can, like x86 and stuff, but not in this. Okay, so how do we? I'm just going to plug the charger in just so we don't run out of charge. Okay, how do we do the next question? What is the next question? I think we're going to have a break here. Question is this. Okay, yeah, we're going to have a break. And then we'll come back and we'll talk about this. So I'll just leave this on. Zoom in a bit. Spend like a minute, stand up, walk around, stretch the legs. I'm just going to do the same. And then we'll come back and we'll get back into it in about a minute or 2 minutes. Just kind of debrief, relax a bit. You've been sitting around for like an hour. Okay, I'll be back in a second. Okay, it's been about 2 minutes, I think, because we stopped about 10:02. So I'm just going to sit back down. Okay, so let's just have a look at this this section here, right? This side break. I'm gonna have a look at how to evaluate this. So I'm just gonna set up the file for it, and we can have a look at that. Okay, so we have a file here that we want to create. We don't need this anymore. And what we're gonna do is we're just gonna repeat this here. We can tell it's MIPS. Okay, and we can start off by defining our X, our Y, and our Z. Right? It says right here that you can presume they're registers or labels in a data set, not registers. I guess you can presume they're registers too. It doesn't really matter, right? The whole point of the question is just to kind of see how you can add them. If they're registers, it becomes very easy, right? Because it's saying how few registers as you can. So obviously that becomes easy, but it's still a bit more difficult. So we're just going to have a word here. Let's say 0. Then this can be a word here. Let's say 10. And this can also be a word here. Let's say 20. Let's make this 5. And let's say it's 133. Sure. Okay. So yes, and we can align the first one by 2, which is going to align it by 4, and then the rest will be aligned by the nature of the first one being aligned, so we don't have to worry too much. Okay, so all we have to do is think about as much as we can, try to group as much as we can. So this is just going to be rental break. I don't know, who cares? Doesn't matter what I call it. So let's just start with the simplest explanation, which is just to evaluate it as left to right. So we're just literally going to do, this, and then we'll times this by z, right? So we're just going to begin with x squared times x squared. So let's load x in. So we're going to load x into 0. I'm going to make this a bit shorter because we won't have that much space, so we won't need that much space. Then we're going to load y into load x into 0, load y into 1, and then we're just going to multiply them by each other, and we are going to need a little bit more space than that. Let's say t0 equals t0 times t0, so that's x equals x squared. Or I guess we'll say like t0 equals x squared. We'll do the same thing for y. And while we're at this, why don't we also load t, right? But here's the problem here is that if we use this, then we'll lose what the value of x is. So we won't be able to use this here. So we'll give this a new register as well, and we'll also give this a new register, right? We're not going to try to keep the registers down. We're just going to try to kind of use as many as we can. So we'll call this temp1, and we can call this temp2 squared. And then we'll have another one, which will be times y. So it'll be t0 times t1. This will be temp3 because x times y. Okay. Then all we're going to do is we're just going to add all 3 together effectively and subtract the last one. So it's just going to be, we'll say we'll accumulate everything into T6. Why not? We'll just not care about registers whatsoever. So the first one will be T3 plus T4. We'll have like accumulator equals x squared plus y squared. Then we'll have, T6 is equal to, we're just going to subtract T6 and subtract x squared minus y squared, which is going to be times 3, which is going to be T5. And this is just going to be accumulator equals x squared plus y squared minus x times y. Then we just want to multiply the entire thing. Z. Accumulator equals z times x squared plus y squared minus x. Okay, so that's like the first step, right? This is like the simplest form. So if we want to actually make this a lot faster, a lot more efficient, whatever, and we'll probably run a bit over time already. What we need to do is we just need to break this up into common parts, right? And so this is often what computers do. You guys don't really have to learn how to do this, but it's just kind of a nice little break from having to worry about like memory addresses and stuff and just worrying about like math. So in this case, we can rearrange as x times, I guess we can just basically grab however many x's we want here. There's a few ways you can do it. The rough idea is that you basically want to reuse registers and you can reload into old registers, right? So what we're going to do here is we can go, okay, let's reload x, right? Also reload y, right? And so this is going to be a second example first. In the second example, we're going to load both these values, and we're not going to load y, z in until the very end, right? Because we don't need it yet. And we're just going to begin with x squared and y squared, right? And so what we're going to do is we're going to say, multiply t0 by t0 by t0, x squared multiply T1 by T1 by T1, right? And notice we're still using just two registers here, y squared. And then we're going to add them together, and we're going to add them together into T2, T0, right? But if we add them, we'll lose what the value of y is. We'll lose the value of x times y. We'll see that in a second. We'll come back to this. Okay, so we'll add T0 and T1. And then all we need to do now, stretch, is we just need to, minus this x times y, right? But obviously, we want to use as few registers as possible. So how do we do that, right? And so the simple answer here is that we actually don't want to calculate this first, because if we calculate this first, now we have to use x and y, means we have to use an extra variable. So we can calculate x squared, but before we calculate x squared here, we're going to calculate x times y, right? So this equals y times x, right? So we can calculate x squared and y times x, and then we're going to subtract them. You can say T0 equals T0 minus T1, which is x squared minus y times x. And then what we're going to do is now we can come back and we can re-add our y in, right? So we're going to reload our y, means we can do y squared, and then we can add them together, and now we have this part. And then all we have to do at the very end is just load z into 1, and then multiply everything again by using the exact same procedure. But this time we'll multiply 0 by z, right? Times. We'll put the z on the opposite side just to show the order of operations that we're doing. Does this make sense, right? So you can kind of use fewer registers. I think this is the fewest registers you can use. Obviously, I don't think you can use one. I think you probably could if you had like x86 or something crazy, but currently you can't. You probably could try to do trickiness if these are all aligned right after each other, like constant offsets and stuff, but I don't really think it's particularly worth it. Wonderful. Okay, so this is your So this is what 5, 8, 10. What's the smallest answer they give? Answers here. The smallest answer they give is 3. So they have a 9 answer, which is okay, but that uses 3 registers, and then they've also got an A8 one that uses 3 registers as well. So they've got 2 answers that are slightly shorter in terms of instructions, but they use 3 registers, and the main reason is they don't have to load this extra y. So they load y into like 2 or something, and then they basically multiply y into like its own register. So like here, and then it means we don't have to use the extra one. So you kind of got that offset here, right? You can trade those two things against each other. You can't have both at the same time. Let's look at the assignment and kind of talk about what you guys are going to be doing for it. So this is a cellular automaton. So effectively, you're going to be having like the game of life, if you know what that is. So you're going to have cells that are alive and cells that are dead. And so what happens is you look in all the cells and you apply a rule depend upon the 3 neighbors, right? So you look at each of the 3 neighbors and you make decisions based on the rule, right? And the rule is pretty well described here. You can look for it, right? And so you can look for all the values and look at all the states and stuff. So really what it is you're just going to store like an array, right? And all you have to do is just operate over that array. So it's really going to test arrays. It shouldn't be much more than that. It will be, a little bit hard because it's your first time doing it, but keep in mind that we basically give you the C code, right? And so all you have to do is convert the C code to the actual assembly and not much else, right? As you can see here, we give you the compiled C implementation. So all you have to do is just basically convert that. And you can use these to check that they're fine. Wonderful. Okay. So I just kind of want to briefly cover that. If you have any questions about it, feel free to ask and I can answer them, but I don't really want to spend too much more time on that. I want to spend the rest of the time on functions calls and going through what the stack is so you can kind of have some understanding for your assignment. So we're going to begin with a very simple example. And we're going to begin with Fibonacci. You know what? We're going to do it this way. And then we're going to begin with Fibonacci. Okay, and here's our Fibonacci code here, right? So Fibonacci is a sequence. It's a pretty straightforward sequence. You're basically evaluating it at each value at either, yes, it uses recursion. We're going to be going through recursion, and we're going to be going through all that stuff when we get these functions, right? So the first thing you got to realize is, what does the stack frame look like? So you kind of start to learn about stack frames, right? So we have a few stack frames here, right? And it kind of looks like a tree. And so I always like implementing them like a tree. So let's just show what they kind of look like if we implement the evaluation of this as a tree. So the first value is that we have, let's say fib of, I don't know, 6, sure. Okay. So fib of 6, look at the cases, what one is going to evaluate to? It's got to evaluate to this second one here. So it's going to do fib of n minus 1 plus fib of n minus 2. So that core is going to split off into a core to 5 and a core to 4. But what does the actual stack frame look like? Well, effectively what we have at the top of our stack, right? At the top of the stack, we have a fib core of 6. Right? Because the stack grows to the left or it grows down. I'm going to grow it down because growing to the left in a document is very, very difficult. Even like graphically, it's very difficult. So I'm just going to make it grow down for the same reason it grows left, right? It goes like negative, I guess. So fib of 6 is going to have two things. The first thing is going to have n here, but I'm going to treat n as a register. So I don't need to have variables unless I want to store these as variables, right? So fib of 6, it does require us to store one of these. We have to temporarily store one of these values before we can move on to the next one. So we'll have to store one of these in the stack. So we'll just call it temp, right? And then this will also then thus push onto the stack. It'll push 5 because this is the first function call it ever makes. So it's going to push 5 onto the stack. 5 will evaluate. In 5, we need to do what? Well, if we build out the tree, it's going to be 4 and 3. Already, I'm realizing this must be a bit longer. So let's do that now before we need to do it later on. So we'll make this a bit longer. Mathematically, that should be enough. If you do it in your head. So also should be longer. We got 5 and we got 4. And we got the same kind of thing, and we can just kind of do by like 3, I guess, rather than doing it by 4. This will be for 4. Okay. So here's our 5 value, and it goes to 4, and we're going to push 4 into the stack. So we're going to come back to this value, but we haven't come back to it yet, right? So I'm just going to leave it empty and put an X here to indicate that we will come back to it, but we haven't evaluated that result yet. And the one thing I'm also realizing is that we do actually have to store this on the stack because we do require it here. So we require temp and we will require n. Right, because we have to come back to do this evaluation. Okay, so 3 here, and then we can do the same result here. Be 3 and 2. And this will also require 2 and so on, right? Obviously, we won't come back to that. We'll come back to that later. Then 3 will also evaluate. So I mean, I will just fill out these. So this is going to have int temp, and it's also going to have n, right? And then we can just do the same thing. And then you can kind of see how this will go. I chose a very long example, so we're probably going to cut this short halfway through, but we'll do like a few evaluations of it so you can kind of see how it works. I think we'll have fib 4 here, which will also do temp and n. Make it shorter. And then we got 3 here. I just copy this. 3 here, which has the exact same result, right? And so you can see that these are pushed all on top of each other. And then we have 2, and then finally, after all this work, right, we finally have only one more result, right, which is going to be 1. And we know here, if it's less than or equal to 1, then we can stop. Yay, okay, so we have 1 here, and we can push 1 into the stack, and this will return. So now this is going to return a value, so I can say like return 1. This return value will come back up here, and we'll push this off the stack. Now temp will equal 1. Right? And we'll make these somewhat line up, and then we can call the next function call, which is going to be 0, right? Okay. And we can call 0, which is just going to be fib of 0. Again, we'll instantly return, right? And so this will pop off the stack, and then it'll add these results together, and then that means that this will return 1 plus 1, right? Which will then pop this off the stack, and therefore this value is now going to equal to 2. I'm just going to say temp, just to make it so it lines up better. Right, and n is equal to 3, I guess. Then it's going to call the next value here from 3, which is, as we can see, going to be 1. Right? So then it's going to call 1, which hopefully you can see is just going to return 1. Right? This is going to pop off the stack, meaning that this now also can return, this is going to return 3, meaning this also pops up the stack. Now we've got a temp value here of 3, right? Meaning that this can then call its next value, which is going to be 2, which again will push onto the stack and then call its next values, which are going to be 1 and 0, right? I'm just going to do like that. Just you gotta get the point, right? So this is going to be 2, and so then this is going to have a value of, well, these are both going to be 1. I mean, they're going to have a value of 1 plus 1, right? Because it's Fibonacci, which means that this will have value of 2. Push this off the stack, which means that this will return 5, because it's going to be 3 from this plus the 2 from this. This comes 5, and so on, right? So the sequence is going to be 1, 1, 2, 3, 5, 8, 13, and so on, right? You add the previous 2 numbers. It's going to get back up here, then this is going to do 3, and it's going to repeat the same procedure. Does that make sense? It's like kind of like these things get popped off, and then it does the next one, and kind of goes back to the function. So how does this actually look like in code? Well, it's right there. So we're going to write it like this, int n. So first off, we have a. So what we're going to first do is we're going to save our return address, and we're going to save n. That's all we have to do, and we're going to save maybe space for this if we get to it, and we need save space for it, right? But before we do any of that, let's handle the return case, because the return case is super easy, right? So we can say, I don't know, branch, just do a really simple thing. So branch less than if n, which is a0, is less than 1, less than equal, right? If n is less than equal to 1, return 1, right? So simple. You just have a simple return here. This is just going to be li v01, and which is just going to be jump r raw. I was going to just say ret there. This is going to be just, I don't know. That's fine. That's fine. We get the point. Okay. This is going to return 1, right? So kind of the more complicated one. So at the very bottom, we'll have to have a JR, right? So 2 JRs here. These are 2 cases. Let's handle the simple one, this case here. So how do we do this? Well, what we first do is we first want to push enough space to save our JR, because we're going to be jumping to things like these functions here, which means that we have to save it for later. So what we're going to do, and there's a few ways you can save things, right? So I think the easiest way here to save, without a doubt, is literally just going to be, we're literally just going to basically move the stack, right? Simple as that. So we're just going to say, okay, I want to move the stack, and I want to make room for -4, which is basically going to make a room for 4 bytes. Because again, the stack grows backwards, it grows negative, right? It grows down. So this is going to make room for raw. So then what we can do is we can do things like this. We can go, okay, now I want to load or store the word rather. I'm going to store a0. I mean, I guess I'll store raw first. Doesn't really matter, right? I'm going to store raw in SP. And then I'm going to repeat this for all my variables. So store a0. Right? And I'm also going to, there's another way you can do this using function pointers, which we'll go into a second, not function pointers, so frame pointers. But I don't really want, that's a bit more complicated, so we'll cover it in a second, but not right now. We'll also need S0 because we'll need to store this value here. So we'll store S0. Wait, this is SP, store S0. And this is kind of like our prologue here. And then at the very end of our function, we basically have to do the opposite and we have to load them back in. So all you have to do is repeat the exact same code that you're writing here, but in reverse. So instead of storing, you're going to be loading. That's it. There's nothing more complicated than this. Just do the exact reverse. Restore, and we'll change this version to S0. So it's going to be restore S0. Then we add 4. Exact same, right? Then we're just going to copy and paste this another few times. So then we're going to restore what? A0, then restore raw. The actual order that you do it in does matter, right? Because this is going to be the top of the stack, so you have to restore it first. Okay, so we're going to store A0, and then we're going to store raw. We're going to restore A0, then we're going to store raw. S0, A0, raw, return. Does that make sense? So we're storing our raw so that we can use it, and then we're restoring it so we can jump back to the function that calls us. Okay, now how do we call this function? Well, the first fib is very easy. We just have to basically go n minus 1. So we're just going to go subtract. We're just going to place that into 0, A0, right? We're going to do A0 minus 1. Right, so we can go n equals A0 minus 1. Okay. So the other thing I'm actually going to do is I'm actually going to swap these two. Just because it will put A0 at the very top of the stack, and that makes it a bit easier because we want to restore it once we do the second part here. So it's kind of a bit easier if it's at the very top of the stack. So you sometimes have to think about it. If it's not, you have to do things like -4 SP, or sorry, rather +4 to like move to the right of the stack. Right. Anyway, so we can go A0, so it's going to be n minus 1. And then we can just call it like this, so we can say fib of n minus 1, right? Because all we're going to do is this followed by syscall. Or no, not syscall. Why am I going back? Followed by a jump and link to fib. Right, so what it's going to do is it's going to basically just do this, right? Okay. So we're just going to jump and link to fib. So what will happen is it will basically change what the raw is, as we know, right? It will move the next line into raw, and then it will jump to fib and repeat. Okay. Now we're back from fib. At this point, we're back. We are done. Fib is finished, and the result is going to be in V0, right? As we can see here, the result's going to be in V0. So how do we use it? Well, we first want to move, right? We want to store S0, or rather we want to store A0 in S0, right? So we want to save the return value, right? We want to save the return value. We're saving this value right here. Okay, now we've saved it, what do we want to do? Well, we want to restore A0, so we can just go load word A0 SP. Restore our arg. And we can repeat the same procedure, but we're going to now subtract 2. Now we're done. All we have to do is just add them together. So we're just going to go add S0 with V0. Right? So add the return value from this with our saved value from here. Okay. And then all we have to do is we have to add those and place those in as our return value. So our return value, right? Our return value will be the return value of this core here plus the saved value of this. Okay. And so neck. Okay. So that's all we need to do here, right? And so this is just going to be our return, and we got our return value here. And so that's it. And then as you can see here, we restore all the values. So for example, if we kind of look at what S0 and stuff is looks here, right? If we look back at this simple example here with this 3 here, so this is 3, and then we push 2 on the stack, right? What will happen is on the stack, it will have temp here, or on the stack, it will have A0. It will also have, A0 equal 3. We'll also have, SP, raw, which will equal whatever address it came from. We'll also have S0, which will in this case equal whatever, right? We haven't said it yet. And then we'll call 2, which will do basically the exact same thing. Actually, why don't we just do 2 here just to make it easier, right? So then we're going to call 1, and 1 is just going to instantly return, right? There's nothing we have to store, so it's just going to return 1. This is going to pop off the stack. It's going to set S0 to 1, right? And then it's going to call the same thing. And then that's going to basically set, it's going to call fib of 0 over, right? Which is going to turn 1, causing this to become V0 equals 2. I'll pop this off the stack, and then we go back to fib3, and then fib3's value will be restored, right? And so that's kind of the point, is that we're pushing in the stack and then restoring whoever called us. So this is kind of saving the values of whoever called us and then restoring their values, right? So they get to use them again. And this will just work, right? I mean, you'd have to put a main function and like a syscall. I'll add all that stuff, right? So you can test it. Okay, so there's one more example I want to do. Because it will be kind of useful for your assignment. And it's also going to bring everything that you learned so far all into one nice package. I'm going to build a linked list in MIPS. So we're going to begin with some simple things. I'm going to kind of explain how this stuff works, right? So we can't actually use malloc in MIPS right now, but not just because you haven't learned it, just because MIPS doesn't really have malloc. It's got something called sberk, which you can kind of emulate malloc with, but you can't do malloc directly. So what we're going to do is we're going to cheat a little, and we're going to place and we have one restriction. I actually clarified the restriction in the question. And the restriction states very simply, we can make the following presumptions. We can only push and pop the top element of the list. Basically, we're creating a stack on the stack, right? But the idea is that we're creating a stack that looks like a linked list, right? So we have like pointers and stuff, but it's just a stack. And we can only use generic push and pop and this apply function pointer, right? Okay, so how do we do that? Well, let's do a pop. Pop is the easiest. So we have head and A0. And so all we have to do, right, is if we look at our data structure here, it's going to be a system call. If you want to do it, you have to do a system call, but you can't do it because we don't give you that system call. So you will never be able to use malloc and MIPS right now because you guys won't have access to that system call, but in reality, you just use the system call. Oh, has next. Yeah, nothing else. It may not always be a system call. It depends how the library is linked, depends what assembly language you're using, but it's the same kind of idea, right? You're jumping to external code. It's not going to be like an instruction. And even sberk is a system call. So if we want to pop here, all we have to do is grab the value of temp, which is going to be the next head. So basically what we're doing here is we're doing head next, right? But remember, this doesn't exist. In assembly, when we want structs in assembly, this is going to blow your mind maybe a little. So if you haven't done structs in assembly, which I don't think you guys have done yet, it's okay if this like hurts, right? It's recorded, you can come back, you can watch it later when you kind of understand it a bit better. But we don't have structs in assembly. So what we're going to do is we're going to create basically 16, or in this case, it's going to be 8 bytes worth of space, right? Because this is going to be 4 bytes and this is also going to be 4. So we have 8 bytes worth of space, and we're going to put that directly into the memory, as you can see here, and we can just write to them as like an array. So we're thinking of this as like an array of integers, basically, right? Where the first integer is a pointer and the second integer holds the data. So in this case, the first integer is going to be next. So we can just say like head of 0, which is just head. Right? So you just literally load the next value. So we're just going to load the next value into T0. Like simple as pie, right? So load A0 into T0. So this is basically going to be just temp equals head, right? All we're going to do is pop it. So we're going to change the stack pointer. So we're going to, by the way, you shouldn't write like real code like this. This is just the only way that we can do this example. So that's going to be pop, obviously, because you're adding, right? In reality, we don't really want to pop function. We don't really want to pop the stack within a function call and then like push the stack within another function because like that's very hard to screw up. Like it's very easy to screw up because obviously if your stack pointer gets like unsynchronized, you're going to be like thinking memory is like a different address than what it really is, and that could get really, really bad. And when I originally was like writing the C code for this, and I actually had like manual assembly in here, I did a few bugs with it, right? As I was trying to get that right. So it is a little bit tricky, right? But it is important. This is the only way we can do it. So we're kind of going to have to resort to this. But I'm just going to put a warning here and say, normally we don't like just adding to the stack. slash pushing on the stack in different functions. And so the push and pop should always be, it's kind of like a malloc and free. Every time you malloc, you're free. Every time you push, you should pop, right? But in this case, we're not pushing, yeah, because it's just like a linked list, right? For a linked list, every time you malloc, you're free. But in a linked list, you can malloc and you can free in different places, right? They can be separate. With us, right, we should always pop when we push, but for us, because it's like a linked list, we can do them in different functions, if that makes sense. So all we have to do is return a temp. So instead of loading into T0, we're going to load into V0 because it's going to be the return value, and then we're just going to jump R. Was that right? Okay. So there's nothing else crazy about this. You can add a 0 here if you really want. Right? Let's skip apply, and we'll come back to that in a second. Let's just do push. So push is going to look like this. Push is also pretty easy, right? We're going to make space in the stack, and we're going to put our variable in. How do we do that, right? Well, the first problem here, right, is if we want to make space, we have to make space. So let's do that first. We're going to add SP, and we're going to add -8. We're going to, I don't know, make room on stack. And by the way, let me know how this goes because we've never run this before. And so we've never like done like a linked list like this before. So if this makes sense and like helps you guys, that's useful. If this is like worse and makes it more confusing, let us know so we can, or let me know so I can like adjust it in the future. I think this is kind of interesting, but maybe it's not. So we're gonna make a room, and then all we're gonna do is we're just gonna store the values. So storing the values is really easy, right? Because all we have to do is say, hey, I want to store A0, which is the head, right? As you can see here, head into S0, SP0, right? And if you don't know how a linked list works, remember what we do is we create like a new linked list element, right? X equals, I guess I'll call it malloc, it doesn't really matter, right? Yes, and we go X and X equals head. Right? And we're just translating that to this. Okay. So we're gonna store it into the stack pointer. Store next. Then we need to store the data. Well, a big mistake is people put 1 instead of 4. Remember each integer is 4 bytes. So I'm just going to put a 0 here just to make that very clear. Store data, right? And then now all we have to do is we just have to move pointer into our V0. Right? Because if that doesn't make sense, let's just think about it, right? So we've made room for the stack pointer, right? We've made room for the LL, which means the address of LL will be at the head of the stack. So wherever the head of the stack is, that's the address of LL. So we've made space for it, we've moved the stack to the left, and then we've written in the next, in the first bit of it, we've written in the data that would one bit after that. So wherever the current address of SP is going to be is address of LL. Wonderful. Okay. So then we're going to jump. Again, we don't need to use any of the craziness that we were using before with prologues and stuff like that yet. We will need to in the future, but right now we don't. Right? Okay. So, and we will test this function, by the way. This is the one that we will test and run because we're going to put a bit more work into it. So let's actually make sure it's right. Let's begin with again another simple one. Printf. So all we have to do is just print out this single n. That's it. Right? Print out n with an arrow. That's all we need to do. Right? And so we're going to load in 1 for printf out a number. So this is basically just printf out a number. Right? Now we could do this, but it's already in A0. So do we really need to move it? No, not really. Right? We don't need to move it. I will still keep it just kind of for those people who are starting off and they're struggling a bit more, right? So you can kind of like look at it and understand that we still have the system call type. We're still loading the arguments. Then we're calling system call, right? Not needed in A1, A0. Okay, wonderful. Let's go next part. We're going to load in the arrow. So it's just putting out string. This stuff is okay. Right. Okay, and then we have a system call. by a jump. Again, we don't need to use any stack here, right? Don't use a stack unless you need to, right? Okay. So now we're at the point where we can't use anything else but use the stack at this point. So we're not going to go to the function pointer because this one's quite complicated. So we're going to start out just our main function. So let's look at what our main function is doing. So it's reading in the list while there's a list, right? Well, as soon as we reach 0 or quotation marks EOF, we're going to stop, right? And then we're just printing out all the lists using this function pointer, right? So what we're doing is this is going to go through every single element in the list and then call this function with the argument of that list element, right? Over and over and over again, and then print out an X to finish the list. And then we're going to accumulate the sum with kind of a local function here, right? So this function here, this doesn't exist in C. So if you try to do this in C, this will fail. This won't compile. You would have to like put the function up here. But the idea is that in assembly, this is kind of okay, right? So I'm kind of showing you some kind of things you can kind of start to see that in assembly, functions don't really exist, right? They're just labels. Okay, we're almost done. There's not much more. It's probably 5 minutes more. So we want to load head in. Yes, so I'm just going to start off by doing a very simple prologue. Actually, you know what? For main, I won't do a prologue. Instead, what I'll do for main is I'll do what we did before, right? Where we like made room for it. Do the prologue for the other function. So we'll just make room for ra, right? And then we'll store ra. So this is not necessarily important for your lab, but it's really important for your assignment, and I won't see you next week. So let's just make sure that you kind of understand what this stuff is doing. I will upload this to GitHub, and I will also upload a video. I'll upload all the finished script. All this stuff will be in GitHub, and you'll be able to run all the examples. I won't be able to do it today. I won't be able to probably. Actually, you know what? I may do it today. I'll see if I got time. Right. If I don't have time today, it'll be done by the weekend. Okay. What are we doing? Why am I adding ra? What am I doing? I'm meant to be adding SP. This is going to be for I don't know. I don't know what registers I want to use, but I know I need to use at least an S0. So we'll just start with an S0 and then we'll come back to it. And we may need to add more, right? I'm kind of winging this a little bit, so we'll see how this goes. Okay, so we're going to load in our head, which is going to be S0, because that's the only one I know I need to use right now. And we're going to call these loops a bit nicer. So we can call this main loop. Right? I'm going to call it load. Because we're going to have so many different functions, right? It's very useful to prefix it with a function name. Very, very useful. Make sure you start doing that, right? Because we're going to have different functions and we may well loop in here. If we have a loop in here and we call them the same thing, that's going to be problematic, right? Because then labels don't matter. This label does not belong to this. This label just is a random label in our code, right? Which is why assembly is kind of annoying to write. So then we can like load v0, right? So we can actually load in each of our integers. So this is our first integer. So this is just going to be, I'm just going to call it getInt. I call it getInt in another program. Just because it's not really like a printf in this case. It's like kind of like we're actually like literally we're like returning a value. That's how we're using it. But I guess you could also say like scanf %d next or something, who cares, right? Okay, some v0. So we can say, okay, if this is equal to 0, right, let's stop the loop. Okay. If it isn't equal to 0, what you can do is you can push it onto the head of the loop. So how do you push into the head of the loop? Well, that's very easy. We push the old head onto the loop. Right, this is our old head. I should have probably said. Right, we push our old head on the loop. And then what we're going to do is we're going to also push the element. So this, and all we're going to do is just ask it to push. Right? But this value returns something, doesn't it? How do we use this value that returns? Well, we use it in the exact same way that we used it in system calls. The exact same way that we use it in Fibonacci, right? We're just going to go, okay, move it, I guess, into S0. That makes sense, right? We're going to move whatever the new head is into S0. So we can't go in like head equals push. Right? Okay. Then that's it. Jump to main loop end. Loop load, sorry. And loop. I always use jump here rather than branch. It's just a habit. It's a bit better. You only really want to use branches when you want relative, like when you want to jump like negative. Even jumping negative here, like this is before, but it's I don't know. It's just a habit I've done. I'll probably keep doing it. It really doesn't matter. Like these are no difference between them. I think the course uses B. I'll try to use B in the future, but I don't really know if it matters. I feel like people can follow that regardless. Okay, so let's begin by looking at how we can finish it. So we're not even going to print it out yet. We're literally just going to pop it back off. Right, so we're basically pushed on to pop it back off. Pop off, right? Because we want to restore the stack. Because if we don't restore the stack, then we can't find what ra is. Right? We can't just like say, oh, I don't care anymore. We have to find what ra is, which means we have to push off the entire stack. And I probably should call this like load end. So pop, and then we'll have like pop end. Right, so we're just pop end is very easy. As you can see it. It is very, very easy, right? We're just gonna say, hey, while our head while the head still has stuff in it, we're going to load it into A0, right? Then we're just gonna call our function. And then all we're gonna do is we're just gonna move new head, as you can see here, right? This returns new head. And we're just gonna move the new head into S0 to pop that off as well, right? There's other ways you can do this too. You could have a counter, and then if you had a counter, then you know exactly how much to pop off. If you know there's like 20 elements, just pop off 20 times 8, right? 160. A loop pop it. Always. Good luck with the math. We don't have much more to go, so you can always just finish it off later. So we don't have, I just have to look at this. Do I want to do anything else? I don't know, that looks fine. I don't really have anything else to do here, that's fine. So what we want to do next is we want to do restoring, and then we'll come back and we'll do the other functions, right? So restoring is pretty easy. We're basically just going to repeat what we did up here. We're going to have S0, right? B. I guess we have to, sorry, I did that wrong. What am I doing? I think you got to add. Then we're going to do the same thing for S1. Well, not S1. What's the next one? Ra. I would think we would have more variables by now, but we don't. We just have two. Okay. Yeah, this seems fine. I have no problem with that. That's fine. And then we have load ra, and we just use ra. Okay. Now the only other thing I want to do now is actually do the functions, right? So this will work by itself. I mean, we could probably try it and see whether or not it works. It will complain about this, but if we just jump. Where are we? Are we in the right directory? So I want to use what? Spim. Oh, there we go. Oh. One, two. It immediately stopped, which is interesting. So it would immediately stop probably here. Let's just look over it and check what the value is. I'm losing where I'm looking. OI 0. If V0 equals 0, then we should stop. I mean, that seems fine to me. Let's just check. So main function, we push L and then we move V0 into S0. That seems fine. So what could potentially be the problem would be our push. That seems fine. We're loading SP. There's nothing necessarily wrong there. That seems good. We may just continue and see whether or not this is something else, but we'll just have a quick look. Might as well, right? So ra and S0, we store head equals null. That's okay. We load 5. We system core. We check for branch. We load A0. We load A1. Sure. We push. We restore. Oh, that's why. It would be useful if I actually did my branches correctly and actually named them correctly, right? We want to loop back around to the top, right? Otherwise, it's not going to work. And now we get a bunch of exceptions. Oh, no, right? Okay, so why are we getting exceptions, right? Okay, so there could be two reasons. but luckily they're not too bad. So here, there's the reasons most likely because we have our pop function and we're doing a pop function wrong, right? So we're okay. Oh, look here. That's why we're still doing the same issue here, right? So the same issue that we did up here, we had here. And the reason why is because we're jumping to end, right? And this was actually kind of intentional, this one here. Um, we're jumping to end. And what's happening is when we're loading in our RA isn't actually going to be a correct RA, is it? Because we haven't actually popped off the entire linked list. So we're actually going to be loading the RA from a different element, which means that when we jump to it, we're going to be jumping to the wrong place. Let's load back in. Let's get the right value. And that's a bit better. It's still giving me an exception, but it's obviously not crashing forever, right? So it could be that we're just loading the wrong value. And we'll deal with that in a second, but it's probably fine, right? It's probably just something else. Maybe we're not like pushing and popping in the right way. I don't know. We load S0 into SP, or from SP we add 4, then we load RAR, then we add 4, and then we jump to RAR. That seems fine. It's probably something else, right? You know, we'll have a look at that later. Let's just keep going, right? Okay, so now let's actually do our main loop here. This stuff here is apply function. To do a apply function is actually pretty easy, right? So to do apply function, all we have to do here is just go, okay, move S0 into A0. And then we can just load in our, like one weird thing here is we're going to load in our printf function. We're loading the address of this function, right? So what that means is that it can use that function as like a function call. And then we can just put, as simple as that. Right, and then the very end, we're just going to add our arrow. Our arrow is super easy, right? We're just going to go print, I don't even know what we call it, and arrow. Then li v04, this is cool. Use that, right? How do we do this printf function though? This one here. Well, this one's a bit tricky, and so we are going to use a classic prologue, just for the simplicity of it. So the prologue begins, and the first thing that we ever do in a prologue, and you can use every single time if you want to do it, right? Is we're going to do a store, and we're going to save the old function pointer. This is not necessarily necessary in this case. It's not necessarily necessary, but we always should do it. Save function pointer, right? Okay. And notice we're using -4, right? Rather than moving the stack pointer every single time that we did down here, we're doing it all at once, then we'll move the stack pointer all the way down the bottom here. Currently, we're going to have to move the stack pointer by like, we'll have to move that 8, right? It's going to be 4 more than this because we have to make room for this plus 1. Okay. Then we're going to load the address of FP. And we're going to load that from, it's a bit weird, from this. What is this actually doing? Well, this is going to load the address of the top of the stack. Right? So this is going to be the very top of the stack. That's where the address begins. And so now from that point onwards, whenever we want to do things like store words, we can always store it from FP rather than using SP. So rather than SP changing over time, we have a consistent thing that won't change. So you want to store this, we're going to store it in -4 FP. We want to store S0, we do the same thing. And we'll also probably have to have S1 because we want a copy of the apply function, right? So, so this should be 8. And this should be -12, right? Then we want to add, and we want to add 16 here, right? 4 more than what we pushed. And then when we remove, all we have to do is just restore in the opposite direction. So what we do is we go add, also this should be -16. And we're going to go add SP16. And then guess what? These all become loads in the opposite direction. So load, 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 load word, load word, load word. Right? And it becomes 12, 8, 4, 4. And it becomes FP, 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 SP, S1, S0, RAR, FP. Then we have our jump. Easy. Okay. So how do we do our loop here? Well, our loop here is pretty easy. We're just going to make copies and copy both our variables because we're going to be using them, right? save variables, right? And then what we're going to do is just going to call a function end, right? Okay. So we're going to first check whether or not it's null. If our list head is null, then we just want to go to the end, right? Else, at the very bottom, we want to jump out back at the top. This is going to go. This is basically it, but it did go for a bit longer than I expected. Sorry. So then we're going to load, and we're going to load A0, right? Because we want to load what the value is. A0. So this is going to load data. So it's going to basically do, temp data, right? Because it's 4, right? If our linked list object here looks like this is address of plus 4. Easy. Okay. Where am I? I'm here. Okay. So then what I want to do is, I guess I'm just going to load the address of the where to continue next. Now we have to do it this way because we can't, because we want to jump to the register of S1, right? We want to jump to our function pointer to continue from there, but we can't both jump to register and link, I believe. Oh, I mean, it doesn't highlight it, right? Just jump and link. I don't think I think in typical MIPS you can, but not in the spin that you have. So instead, what we have to do is we have to do it out manually. So we're going to load ra to some continue label, which can be done here, right? And then we're going to jump to the function, and then once the function ends, it's going to go back here, right? So once back here, we can just load S0, right? It's going to be temp equals temp, and then we can just jump back to the loop, right? So basically, this is like temp equals temp next, I guess. Right? Okay, and that's just going to loop forever, and now we're done, right? We run this, right? We get a exception, but we're still printing stuff out. That's pretty nice that we're still printing stuff out, but we are getting exceptions. So why? Well, probably because of our loading codes. Let's just double check and look over it. It's going to be something small. That seems fine. For sure. And then we're going to set head now. That's okay. I'm fine with that. That's fine. We're going to load in 5 system core. We're going to jump to the end if it's 0, else we're going to move to A0. Oh, there we go. Right. Okay. Let's do a crazy big list. The one big thing you notice is there's no upper limit. I think I entered a blank space, so did that. Okay. Let's just go back to it and retry it. Right. So we see this, we're going forever. Right, until we run out of stack space. I'm not going to go forever, but I'm going to stop there. And look at that stack. Look at it, right? We built a very beautiful linked list in MIPS. Okay. And for the final example, the lap around the course, we'll just do the simple sum, right? Okay, so the simple sum is going to be pretty nice. We just have a sum variable right here, so we can just use that. So all we're going to do to do this simple sum is we're going to load the address of it. I guess we should load into like S1 because we want to like, let's not even use S1. Let's just use a trick. We're just going to go, remember I told you about this trick before, right? So we're going to store to sum 0, right? That's all we're going to do. Store into sum 0, and you can do this if you really want, right? Okay. And then what we're going to do is we're going to jump, and we're going to go, okay, we're going to load, because again, we have to do the same continue thing, right? Because we can't, we want to jump to a function, right? So we have to like jump and link, but we want to like, the point at which we want to continue is not going to be the next line, right? Because we're going to have our local function right here. And this local function, quotation marks, is going to have int n. And it's going to basically just sum. So the sum is very 0, easy. It's just going to load the address of this, right? And then it's just going to add to it A0, right? Again, should be pretty fine. Like, it's just going to go like sum is plus or equal to n, right? And then it just says to store it back in. Right? So we're loading, we're adding, then we're storing, and then we're just jumping back. Right. And so if we want to do this, we want to be able to jump over this function. Otherwise, it's just going to go to the next line here, which is wrong. So to jump over the function, we're going to have this main continue here. Then we're just going to load the address of main continue into that way we can, for example, move our rest of our arguments. I guess we have to do this as well. We have to also load the function we want to call. But this kind of shows you that these functions aren't special, right? They're just labels. And then we're going to jump to apply. Right? Okay, now once we've done that, we can print out the sum. I'm just going to print out some text. Right, it's going to go. Score. Then we just have to load in the values. And this will be it. We did run an hour overhead, sorry. But I feel like this is kind of useful. Like we built a real example, and you can look at this example when you're building your code. And this real example shows you both methods. Like it's kind of realistic. You can play around with it. You can add your own functions. It shows you function pointers. Yeah. Continue. And we'll use this one. The reason why I'm writing this is just to make it clear that once this function is ended here, we can still use our S1, right? This is saved, right? So there's nothing stopping us from using it if we have an S1. As I said before, instead of going to the S1 route, which is I was originally going to go for, I had a note here saying go for S1. Instead, we don't need to do that. We're to reload in. We're just going to say load A0 into sum of A0, right? Save this as a register, makes things easier. And then we can just go print out the value. Easy as that, right? And then at the very end, we can just also print out a /n. And syscall. And then we're done. See a beautiful sum here. Now, do you have any questions about this? Any kind of any thoughts and stuff? The one I would recommend for your assignment is probably just to do this. I think this is the easiest version. You can add, you can remove from it as you needed. If you really want to go crazy, you can do prologues. What I will say is that I did this course, I did quite well in it, and I never use prologues, ever. Like, you don't need to use them to do well. I don't think I've ever really heard of someone using them in a final exam. They're just so much effort. You should know that they exist, but you don't really need to use them. I don't really think they're useful when you're coding professionally, but for all the stuff you're going to be doing this course, it's not that useful. Just don't waste that time. Where can find codes later on? Easy. Okay, so these codes will be located at the same address. I will do the push right now. So the codes will be everything I've done so far will be up there. It's just they may be they won't have like main functions and everything. There's two ways you can get it. Depends on how much you like it. So the first way is here, right? So I'll put this link in. You can just click this little guy here. He's got a really cute animation. So cute. Okay. And that will give you to this page, and I'll post this page in the chat. And this page here, you can just go to Tute5, and all the files will be right here. You can just download the files or whatever you want. Some of my students in the past, especially for things like courses like 2511, where you start to learn like, wow, they've completely changed the look of this. I haven't looked at GitHub in like a week. They do to it. They freaking destroyed my boy. What is this? Anyway, there's this clone thing, right? And so you can clone it, and the benefit of clone is that you can just pull down the changes every time this changes. So every time I do a new thing, you could just like pull down, and you'd have like local files of it, so you don't have to keep downloading the files. But if all you're gonna do is look at them, that's fine. I mean, there's also other stuff here. These are from other courses, but I will just kind of keep them in the same place just because sometimes they're relevant. So if you want, you can like look at some string algorithms, and you can like go them by hand, or you can even look at the very cursed 234 implementation. If you haven't done 2521 yet, when you do it, just keep in mind that the reason why we don't show you a 234 tree, the reason why we don't show you the implementation for insert is because it looks like this. Look how many freaking cases that this was a nightmare to build. An absolute nightmare. And there could even be a bug with it, right? It's just kind of like a general layout of what it would look like. That was not worth the time. Anyway, so there's all that stuff there. There's also instructions on file.io if you need a recap on file.io. There's some example here that goes through some examples. Again, this is just an accumulation from a few years of doing stuff. Anyway, thank you all. We can go to the lab now. I'm sorry for taking up 2 hours of time. And if you have any questions, obviously you can raise your hand and ask. I'll stop recording.